Alright, what's up guys? In this video we're going to pick up with some partial differential equations. We're going to be talking about the two-dimensional Laplace equation. So we're asked to show that the given function satisfies the two-dimensional Laplace equation. So we're given this two-dimensional function f of x comma y is equal to e to the negative 2y cosine of 2x. So the Laplace equation is one of the very first partial differential equations that you'll learn about. There is a three-dimensional Laplace equation. But we're just going to do a problem here with the two-dimensional one. And so remember, the Laplace equation is just del squared f partial squared f over partial x squared plus partial squared f over partial y squared. And that's just going to be equal to 0. If it were a three-dimensional Laplace equation, it'd just be an extra variable. So this is going to be the Laplace equation, and like I said, this is one of the very first partial differential equations you'll learn about, along with the heat equation, the wave equation. Since I have a physics degree, I've worked a lot in the past with Laplace equation and all the other types of equations as well. Okay, so basically what we're going to do is we need to take this function, and what we need to do to verify it is we need to take the first set of partial derivatives. So we need to take the first partial derivative of this function with respect to x. We'll need to take the second partial derivative of this function with respect to x. So we'll need the first partial derivative and the second partial derivative with respect to that variable. Same thing for the y. And then what we do is we take the result that we get for our second partial derivatives and we plug them into this Laplace equation here and see if it equals 0. If it does, it satisfies the equation. If it doesn't, it does not. That's basically kind of how it works. So let's begin by finding the partial of f with respect to x. And so what we'll need to do is take our partial derivatives. Okay, so to do this, you got to make sure that you know how to take partial derivatives, and also make sure that you are aware of all your derivative rules and things like that, obviously. Otherwise, this won't be too fun. So just make sure you're cool with that. So if we look at this function here with respect to x, what will be our derivative? Well, if we take the partial here, that means we're treating y as a constant. So it looks like we're going to get negative 2e to the negative 2y multiplied by sine of 2x, and all I did was bring the negative to the front, just in case you were wondering. Now, why did we get this? Well, e to the negative 2y, again, since we're treating y as a constant, we're basically only concerned with the cosine of 2x. Now, we know to differentiate the cosine of 2x, we would apply the chain rule, which says that we take the derivative of the outside function, leave the inside alone, multiply by the derivative of the inside, which would, with respect to x, which would just be 2. So since we know that that would be negative sign, all I did was bring the negative to the front, and I also took the 2 that we would have gotten when we took the derivative of the inside, or multiplied by the derivative of the inside, and I just brought it to the front. So that's why the answer is what it is, just in case you were wondering. And now we need to do it the second time now. So the best thing to do is to pull out constants and get that out of the way, and then take your partial derivative, and then you bring those constants back in and multiply them through. So for our second partial derivative here with respect to x, we'll get negative 4e to the negative 2y, and this goes back to cosine of 2x, because we're treating y as a constant. So that's our second partial derivative. Now we need to do the same thing for y. So we need the partial of f with respect to y. So this time we're treating x as a constant, unlike what we did the first time. So since we're treating x as a constant, we're really only concerned with this e to the negative 2y. So if we take the derivative here, we'll get negative 2e to the negative 2y. The cosine of 2x goes unchanged because we're treating it as a constant. And the reason for that is because remember that the derivative with respect to y of e to the negative 2y is just negative 2e to the negative 2y if you apply the chain rule. And then we just need the second partial derivative as well. So let's get that one next. Same thing here. The only difference is when we do it this time, again, we'll take the partial derivative with respect to y for e to the negative 2y, which would be negative 2e to the negative 2y. But the negative 2 is a constant. Imagine that we pulled that out. We've multiplied two negative 2's together, gives us a positive 4. So this would be positive 4 e to the negative 2y. And again, we're treating x a constant, so the cosine of 2x goes unchanged. Now, to validate whether or not this satisfies the two-dimensional Laplace equation, all we have to do is substitute it in. So it was second partial f over partial x squared plus second partial f over partial y squared. So all I have to do is substitute it in there. So we'll substitute in our partial derivatives. So it'll be negative 4e to the negative 2y cosine of 2x. Then we'll add that to our second partial of our function with respect to y. So that would be 4e to the negative 2y cosine of 2x. And as you can clearly see, this will clearly subtract out to be 0, which means that this function, in fact, does satisfy the two-dimensional Laplace equation. So that would be your answer. So your final answer for this, our function f of x comma y is equal to e to the negative 2y multiplied by cosine of 2x. We can say that it does in fact satisfy the 2D or two-dimensional Laplace equation, and that's basically how it kind of works. And that's your answer. So I'll do another one of these where we do it with the three-dimensional Laplace equation. It really wouldn't be any different if we did it with a three-dimensional Laplace equation. It would just be an extra variable. But I'll also post a video where we'll work with both the heat equation and the wave equation too. Those are pretty cool partial differential equations to work with. So that's your answer for this. So let me know if you got any questions, but I'll see you guys next time.